Good evening, everyone. Melinda speaking here on behalf of FOSI Committee. It is my pleasure to welcome you here tonight in FOSI Online Talk series. Stay at home and keep physical distancing. I would like to extend my gratitude to our sponsor, Noble Energy Resources, for funding this Zoom platform. With us together, I see from the participants list, Mas Ricky, our General Secretary of FOSI, Pak Win, our advisor, and then Mas Erlangga, I also see joining us today, and the rest will joining us soon. We're glad to inform you that we established the FOSI YouTube channel. We uploaded all the videos from the previous talk already, and don't forget to subscribe and like the channel, and please enjoy the video. And today's talk will be uploaded as well. The committee is always trying to keep the consistency in organizing this online talk series. Then we can learn together through this platform. Therefore, we are more than happy for feedback and suggestion from you all. I would like to thank you for joining us. Get ready to be excited for a while because the topic should be really interesting to be discussed. It's all about basic to advanced method. The topic will be from outcrop to 3D reservoir simulation, an example of analog reservoir studies. The registered participants is almost 100, so we're waiting the rest to joining us. Moving right along, it is now my pleasure to introduce our guest speaker. Really honored to have Mas Ivan Praja from Rockford Dynamics. Many thanks for sparing your time this evening, Mas. I believe most of you know him very well, even met him. Later, I will let Mas Ivan to introduce himself to you all again. Mas Ivan will share the materials. Later on, we'll discuss further about this for our documentation. If anyone needs the material, please wait until the end of the session. We will send a bit later. Well, before I hand over to our guest speaker, as usual, please allow me to give you some rules in order to make this meeting running smoothly. I would like to get your attention for a moment. I recommend all participants to mute the audio and switch off your video during explanation from presenter to maintain good connection. The presentation may be recorded for screening within the FOSI platform. A Q&A box can be found in the icons panel, usually at the bottom of your screen. Enter your name to the committee to collect after the presentation. It will be answered live. Later on, you might turn on your audio and video to deliver your question. And for this presentation, let's see how many questions arise. Later, I will let Mas Ivan to have a break. Maybe if so many questions arises, then we can answer the question in the middle of the presentation. So, well, ladies and gentlemen, enjoy the talk and please welcome Mas Ivan.
Thank you, Mbak Melinda. Thank you all for coming here today. Thank you, FOSI, for having me. Today, I hope everyone stays safe and healthy during this time. Today, I want to talk about something that can be a solution for geoscientists who cannot get out to the wild due to the pandemic, of course, and that is utilizing the virtual outcrop or 3D scan outcrop for various studies. But tonight, I'm going to just present one of the examples, which is reservoir analog with virtual outcrop. So this is me. I'm Ivan. I'm a geologist at Rock Flow Dynamics for Southeast Asia region. I've been working as a geologist since 2012. I got my master degree from University of Aberdeen. And actually part of today's presentation is basically what I had written during my master thesis. So for today's agenda, first I'm going to introduce you to the virtual outcrop. Then we're going to have a mini virtual field trip to Blue Cliff, Utah, USA. And we're going to build a 3D model from the outcrop that we are observing in the virtual outcrop. And then we're going to simulate it and then later discuss the result of the simulation. And at the end, we'll have a Q&A session. So short intro then. So outside of Indonesia, virtual outcrop is quite popular actually. There's a SafariDB, which is a research collaboration between Norwegian Research Directorate, or NPD, University of Aberdeen, and European companies. They have 200 plus filter outcrops. They also provided me with the filter outcrop, which I use for my master thesis, basically. So how does it look like, the filter outcrop? So this is how it looks like. It's actually a 3D surface on which typically a high resolution image is draped onto. And depending how detailed we wanted the filter outcrop to be, we can use combination of LiDAR, high precision GPS or DSLR, and alternatively, we can use drones to for a lower quality result, but sufficient enough for a typical reservoir analog studies. From the LiDAR or drones, we can make point clouds and then triangulate them to make a 3D surface like so. And then we can drape the images from the outcrop onto the 3D surface. This is an example which I took from YouTube. So from a drone, we can have images with their respective coordinates and altitudes from which they were taken. From those data, the software will analyze for the pixel depth and generate sparse point cloud. From there, we can remove all the noises, vegetations from the model, and then calibrate the coordinates with GPS data. Like so. And then after that, we can create high density cloud and then color code the point cloud. And then finally, we can drape the images. So it's quite a straightforward approach to create a filter outcrop. So I'm going to let the video play here. So here it's shown that the model is calibrated to the GPS, and then we'll then create a high density point cloud like shown here, and then drape the high resolution image from the drones. Okay then. Again, depending on the tools which we use to scan the outcrop, they can be really detailed, as shown on the graph here. So they can be as detailed as centimeters for the resolution, so they can resolve the lamina or the stratigraphic features like cross-stratification and extra. So by observing and studying filter outcrop, we can create pseudo-logs, pseudo-sedimentary logs. We can digitize the stratigraphic surfaces and export them as polylines ASCII, and then carry it forward to the 3D modeling software or anything that you want to do with the polylines ASCII. So this is the typical workflow for a reservoir analog studies with filter outcrop. First, we prepare the data, the filter outcrop itself, and then we're going to calibrate the filter outcrop with sedimentary logs that we created in the field, and then integrate them. And then after that, we can interpret the lithologic and stratigraphic boundaries, and then digitize the pseudo logs. And then we can also extract the quantitative data such as bedlag and thicknesses. And then we can also measure the strata orientations. From there, we can carry it forward to the 3D modeling software and use them as the input for the 3D modeling. So let us have a quick field trip to Book Cliff then. So we're going to pretend to fly from Indonesia to Utah. So I'm going to pause it there. And to the west here, we have the mountain ranges of Sede Organic Belt. And to the east, we have the low-lying Cretaceous sediments, which makes the bulk of the Book Cliff. So this is the approximate location of Book Cliff. And these features are the manifestation of a foreland basin. Let's continue a bit. This is the geologic maps of Utah. And let's zoom a bit to the one of the cliffs here. Okay. Even with the Google Earth, we can clearly trace individual sand packages here, and therefore booklet is very popular among geologists and sedimentologists. I even have been told that this is also where sequence stratigraphy was born, or at least becoming more popular after the work of Van Wagener and Exxon production research in early 90s, which was recorded in the IAGI memoir number 64. You can see here that Van Wagener created a quite extensive correlation plate. Yeah, and then we're going to build upon his studies, but we're only going to use several part of it, not all of it, for tonight. Just for basic knowledge, we're looking at the late Cretaceous geology of Utah. So basically, in the late Cretaceous, Portland Basin was formed and created a Western Interrail Seaway, stretches along the middle of USA here. And in the basin, the most sediments of Mesophilic group interfinger and pass laterally into the offshore marine deposits of Mancosial formations. So the Mancosial formation is the gray part here, and the Mesophilic group is the non-marine and marine part of the yeah. So we can see more clearly here in the fourth order sequence stratigraphy of Mesophilic group, where typically a coarser grain sediments here from the west passes laterally to the east into the shelves of Mancos formation. So for today, we're going to focus to the desert member, D1 and D2, and the non-marine part of the tidally influenced fluvial estuarine environment above the DSB or the desert sequence boundary. From that extensive correlation that Van Wagener produced, I took a portion from it, and these are the locations. So only from number 15 and number 58 that I'm going to build upon. So this is the fifth order sequence stratigraphy from those sedimentary logs that Van Wagener produced in 1995. Generally, there are two environment here. The first one is the wave-dominated delta and the tidal estuarine, which sits above the desert sequence boundary, marked in the red here. So I did not change much of the interpretation from the wave-dominated system sites, but I only focus myself on figuring out how to do a correlation on the tidal estuarine system particularly. So that is what sets me apart from Van Wagener in 1995. So for the wave-dominated delta, it's classic. The coarser grain of foreshore facies here passes laterally into shells of the offshore area. And for the estuarine system, vertically, we typically have subtidal bars marked with pink here, and then intertidal heterolithics marked with green here, and the supratidal mud, which is colored in dark green here. For correlating the wave-dominated delta, it is a matter of identifying parasequence and mark every reversal of sequence. But what is interesting is in the tidal estuarine environment itself. And what I found is that by studying the virtual outcrop, we cannot always rely on stacking patterns to define a correlation surface in the tidal estuarine environment. And I'm going to talk about this more on later on when we get to take a look at the virtual outcrop. Now, the thing to note is that in the west here, the net growth is fairly high compared to the eastern part here, where the net growth is worsened. Okay. Okay, if I do not have a virtual outcrop and I only have those sedimentary logs from the field, can I still make a reservoir analog for studying the field? The answer is yes. So I'm going to show you how. First, we're going to transfer the correlation plate. to the 3D modeling software here, and we can import all the logs, and then we can interpret for the fascies, and then we can interpret for the markers. And then later on, use the sedimentary logs as a pseudo wells. And then after that, we're going to use the markers as the basis of building the horizons. And from there, we can create the 3D grid. And then after the 3D grid is created, we can fill the 3D grid with the fascies. And with that, we have the 3D models that we can use later on for simulation purposes or just studying the fascies throughout the field. Okay. So remember how the corrosion plate with the NTG is getting worsened to the east. Here's how it looked like on the field. So to the left here, we have lots of sands, but not so much in the right picture here. So, and the dark gray rubbles here is the shells of Mankosh Formation. And that is the first fascist association that we can identify on the field. And so then let's identify more fascists on the field then. Up tip from the offshore shell formation, we have the offshore transition zone. And the offshore transition zone comprises of sand and shell interbeds with occasional wave ripple or low angle cross stratification here. Next, we have lower surface fascies, which is typically amalgamated, massive, and sometimes exhibit hammocky cross stratifications, like shown on the top left picture here. Next, again, up deep, we have the foreshore and the upper surface fascies, which are even coarser in grain sizes, and due to the high porosity and typically, they are typically bleached, which resulted in the what's so-called the white caps, as pointed here in the picture. They typically have planar or cross stratification and curves also. Now we get into the S1 system, and we can start with subtidal sandbars. In terms of reservoir quality, this is probably the highest quality among all of the fascies inside the S1 system. They are typically stacked and exhibit curved ripples as shown here, and sometimes herringbone cross stratification is up here, but it's not quite clear. Okay. Next in the tidal estuarine system is the tidal heterolytic fascies and supratidal mudflats. So the intertidal heterolytics are typically found with naturally dipping layers of sand and shells here. And the shell is due to the influence of tidal energy mixing into the river-dominated system. And for the supratidal fascies here, they usually comprise mud and coal. So that is all there is for the desert member. Now let's take a look at the filtral outcrop. So for the filtral outcrop, we choose to scan a cliff, which like 50 meters behind the cliff, there is a well that was drilled by the Exxon Production Research and Van Wagener in 1995. So we can have quite a comparison between what is look like on the outcrop and what is look like on the well side of it. So for your information, this filtral outcrop is 1 kilometers wide and 100 meters tall. South is to the right and north is to the left, and we are looking directly to the outcrop in about east direction. With the filtral outcrop, we can digitize polylines on the surface, like I'm going to show you in the video here. And we will have the XYZ from each of the digitized points, and then we can calculate the bed thickness and length based on that coordinates. We can also export the lines as ASCII file. And not only that, we can also measure the orientation of the bed as shown here. Okay. Okay. So we are going to digitize 3 points from which the software will create a plane like so. And then from that plane, the software will know the dip and strike of the planes. So we're going to stretch the vertical exaggeration to 200%. And then we're going to scroll around the vector outcrop from now on. So here we can see the shells at the bottom part, marked with the gray area here. It's not quite clear, but it's there, the shells marked in gray. And above that is the thinly bedded sand and shells from the offshore transition zones shown here. So there is a unique feature within the offshore transition zones, which I'm going to show you in a minute. Right. Okay, let's scroll to the right. And okay. If you see onto the offshore transition zone here, which to the left is thinly bedded sand and shells, we can see some kind of channel-like features as highlighted with the cursor here, the mouse. And we have even more to the right. These shapes are not distributally channels, but these are more probably related to the strong rip current during the storm era, and then the coarser sediments of the upper surface and lower surface are carried by the rip current to the offshore transition zones area with that rip current. Okay, let's see to the left here and trace one of the lower surface faces. And above that, as we see here, there is a thickly bedded sandstone here. And that is the lower surface facies seen on the virtual outcrop. And these are also lower surface facies, but they are thickly bedded and amalgamated, so they kind of obscure the flooding surfaces between them. If you trace the individual lower surface facies here, you can scroll to the right, we will see more and more thinly shell intercalations. And then again to the right, more shells intercalations in the lower surface facies, and then finally we'll pass into the offshore transition zones with thinly bedded sand and shells. Okay. Going to move along. So next is the upper surface facies, which marked with the white caps, as in the outcrop here. And now let's trace the top of the lower surface facies here. So it seems like a flat normal surface and conformable, but let's trace it to the right here, still flat and conformable. Okay. Finally, to the right, we will see some kind of erosional surfaces there, on which coarser sediment sits on top of it. So this is not quite a sequence boundary, but it's close. But it's most probably the extension of the features that we saw on the offshore transition zone, which is rip current features of the wave-dominated delta system. And both that erosional surface created by the rip current is deposited the coarser sediment eroded from the upper surface to the lower surface facies. Okay, let's move to the top of the cliff here and trace the top of one of the sand here. You can see that from here, the top of the surface, top of the sand is flat and conformable, but quickly passes through to the erosional surface here. And you can see above the erosional surface, the characteristic of the sediments are quite different, which those below it. So now we're quite sure that this is the sequence boundary. And sits above the sequence boundary is gently dipping amalgamated sediments or sandstones of subtidal bar. So you can see here the stacked subtidal bars and the shells from the tidally influenced environment. And above the subtidal bars are the intertidal hydraulics, and above that you can see coals and mud. Those are from the supratidal mud flats. Okay. Okay. If I pause here, what I found is that there is this termination surfaces. As you can see here, these termination surfaces, it's actually correlatable, or I can observe this termination surface throughout the tetra outcrop. Let's see to the right if the surfaces still exist. So yeah, we can trace the termination surface from the left to the right here, even to the right-hand side of the outcrop here. And those termination surface are actually the surfaces that I'm looking for when I'm trying to correlate within the tidal environment. So okay. So then I use the these termination surfaces as the correlation surface within the tidal estuarine system, and above that you can see is the supratidal mud and coal. And above the coal is another wave-dominated deposits or lower surface facies, and above that you can see another big erosional surface on which the braided channel of the Castle Gate Formation are deposited. But we are not going to focus ourselves on the braided channels from the Castle Gate Formations. Okay. So based on those observations I made on the tetra outcrop, I can digitize the all the stratigraphic surfaces. I can digitize the flooding surface in green here. And the red is the sequence boundary, and the blue is most likely the maximum flooding surfaces. And I also can digitize individual rip current channel features, which we discussed earlier. And then I can export them and have them imported in the 3D modeling software that I chose, which is the Navigator. Okay, I wrote a slide here, but in summary, we have several observed facies association. The first one is offshore transition zones, and then lower surface. The fourth one is subtidal bar, which sits on top of the sequence boundary here, and then another facies in the estuarine system is the intertidal heterolytics, and the last one is the supratidal mud and coals. So for the wave-dominated delta, this is the conceptual deposition system. It's fairly classic. And for the, sorry. And for the estuarine system, I made it myself. So we have mixed energies from river and tidal influences. And it is shielded from the wave-dominated system outside of it due to the funnel shape created in conjunction with the sequence boundary. So learning from the virtual outcrop, we know that the termination surface is probably most equal to the sea level rise, and therefore we can use them as corrosion surface in the estuarine system. And in the logs, we probably can define this termination surface by abrupt changes in orientations of the beds. We can see it from deep meters, FMI, or borehole images. And we can use this surface in the modeling also to create more realistic zones for the flow simulations. So let's build the 3D model from the outcrop then. First, we're going to set the horizon and layering settings to closely match what we've seen on the virtual outcrop. This will call, for this model, we'll call it the dipping grid model or inclined grid model. And for a fun experiment in the name of reservoir analog studies, we are going to make another model in which we are going to pretend that we do not have much data and it is under-informed reservoir studies. So we're going to just make it layer cake models and see how they compare later. So I'm not going to talk much about the dynamic modeling part of the studies, but these are what I need for dynamic simulation purposes. So there are pivot tables, relative permeability curve, equilibrium specification, compressibility, rock and well structure and story, and development strategies. If you want to replicate these studies, here are the parameters that are used for the dynamic simulations. Later on, if this uploaded to YouTube or you have the materials, you can copy this for your studies as well. So to build the model, again, we're going to start with moving the correlation plate to the software, but also this time we have polylines from the virtual outcrops. And then we're going to build the horizons, build the 3D grid, setting the layer for each of the model, and fill them with facies and properties, and set the dynamic simulations parameters. So here we're going to create the structural model, adding the horizons, build the horizons for the structural models, and set the layering settings. And we are going to create the grid, which we're going to try to closely match the features on the outcrop. And we're going to fill them with the facies, with TGS and porosity with the help of HGS. And then we're going to set all of the dynamic parameters here. Okay, just in the equilibrium, the relative permeability, compressibility, fluid mapping for the PVT, critical well permeability, and then and after that we can run the workflow, and from there we'll have the horizons and the 3D grids, which closely match to what we have observed on the Sept From Outcrop. And there's the FOSI model, and this is the porosity. And finally, if we take a look at the model itself, when we compare to the polylines that have created by using the Sept From Outcrop, you can see that the model is quite matching the Sept From Outcrop features. Okay, now we have two models which more or less capture the same FOSI distributions, but carries different grading strategies and thus different geological concept or correlation concept. The question to be asked is, do they exhibit the same sweeping profile? To find out, let's discuss the result of the simulations. No big surprise here. Both models exhibit basically quite different result. The layer cake model did not have to rely on the vertical permeability of the permeability for the fluids to flow, unlike the dipping grid model here. And we can see that early water breakthrough in one of the in the process of wells in here. So we have one injector wells here set up and two producers, P2 and P1. Okay, if we compare the projection rate on the field scale, we can see that both models are quite similar in terms of projection rate with the regular grid model almost match those of the dipping grid model. But then if we take a look at the well scale, we can clearly see that visually, we can clearly see what we visually saw from the previous, where the water breakthrough reached the one of the wells earlier in the dipping grid model. So if you take a look here, the early water breakthrough is not compensated well in the regular grid model. But can we push our luck and try to match the regular grid model for history matching? Yes, is the answer. So we can modify the relative permeability, the dynamic parameters of the model, and we can go as far as do a manual editing to the permeability here. So it's look like a Dalmatian dog here with the models. If I'm the geologist, I'll be asking my reservoir engineer, are we playing Tetris here? Because it doesn't look like something that is geologically viable or can be explained with a normal geological common sense. So yeah, in a field scale, of course, we can match the regular grid model. But then if you take a look closer again at the well by well production rate, of course, we cannot compensate that early water breakthrough from the regular grid model. If we forecast them in 5 years, there is now a 7% difference. And what is dangerous is when we use the geologically wrong model to make a forecast and make an economic decision based on the forecast. That's with 3 wells, so one producer and 2 producers, sorry, and 1 injector. Let's add another infill well just for fun. Now the difference is 9%. So with only adding 1 well, it adds 2% of errors. Of course, the results may vary, but this is quite concerning actually. So for the takeaways, Sept From Outcrop provided a platform for geoscientists to confirm their imagination. And what we can do with Sept From Outcrop is actually quite extensive. We can use it for geotourism. We can use it for field trip, like what we did earlier, especially during this pandemic time, where we cannot go out to the wild, and we can use it for knowledge studies, database for the sedimentary features. In the mining industries, they use it for reserve estimation, and even in the Netherlands, they use the LiDAR data for the land geotechnical analysis, because they're dealing with the land that is lower than the mean sea level there. And for the Sept From Outcrop studies for the incised valley field, which is which commonly comprises of tidal estuarine deposits, but sometimes it can also be just shale scar in the tidal environment or tidal estuarine environment. And the storage surfaces or strata termination surfaces is equal to a sea level rise. So we can use them as kind of flooding surfaces and corrosion surface in the estuarine system. No big surprise here. The last takeaways is the different geological concept. Maybe it's different from structural or stratigraphic point of view. They resulted in distinct 3D grid realizations, which in turn resulted in a different flow simulation characteristics. So no big surprise, but we can tackle this with the fully integrated reservoir studies that lets you experiment and find just the right balance between what is viable engineering-wise and what is geologically makes sense. So that's all for my presentation. We can go on to the question and answer session. Thank you.
Okay, thank you, Mas Ivan, for the nice presentations. Very nice outcrop, yeah. We're still waiting for the questions. Unfortunately, there is still empty slot here for the questions, yeah.
No problem.
Anyone want to have a question? Please, can you can put your name in the chat box, yeah, if you want to know anything from Ivan. Yeah.
Sorry, just taking a sip there.
Yeah. Okay. The first one we have from Pak Win. Pak Win, you can turn on, please. Yeah.
That's a great presentation. I have to admit I'm a bit weepy with nostalgia, because when I started with Exxon in 1979, we had classes from Van Wagner, and we knew he was going up and down Book Cliffs, and we took a field trip out there. So man, this takes me back, way back. Let me ask you a bit of a loaded question. Some of my foggy memory seems to tell me that in Book Cliffs, if you're at the right part of the outcrop, that one part of the outcrop is essentially a strike section of the system, and another part of the outcrop is essentially dip. So when you do your 3D modeling with the outcrop face, is all of that essentially compensated for, or do you as the geologist have to recognize and put those concepts into your model? Thank you again for the great talk.
Yeah. Okay. Thank you, Pak Win, for the question. I'm going to start to answer with. So we have a general depositional dip to the east here. So if we take a look at the map in the book clip, so we have the depositional dip to the right, and then the positional strike is to the north or south here. So from there, we can know that if we walk to the east, we will see the sand getting thinner and thinner, and later passes into the shales. And then we will recognize more and more lower surface facies and offshore transition zones towards the east, and then towards the west here, we have more sands and more upper surface facies. So then what I did when I'm doing the modeling is I transfer the correlation plate that I did in the depositional dip direction, and then from there I just interpreted for the facies. If you can see here, more and more to the east, more and more sand is gone. And then from there, I can use the truncated Gaussian simulations to spread the facies and the throughout the entire field. So that's how I control the sedimentary facies distribution within this 3D model, Pak Win. Is that hopefully that answered your question?
Well, if I'm hearing you right, you did take it into account, and basically the model there has to be the human interaction and recognition. You can't all do this by AI. It can't all just be digitized and then put out. The input is coming from the geologic concept that you're interpreting on the outcrop. Am I saying that right?
Yeah, very true, very true. And we can control it by the sedimentary logs that we created here. And also if from the field, I saw that like, for example, on this cliff, I didn't see, for example, foreshore facies, but in the model I have foreshore facies. I will then just manually edit the models and add to the trend, probably to control, to better control the facies distribution when doing the 3D modeling.
Answering your question.
Yeah, no, that got it. It's a great outcrop, and it's a great study. Truly a classic. It almost should be required attendance by every geologist, either by foot, which is quite a hike, or now as you've done by virtual outcrop. It's fantastic. Thank you again.
Okay, Pak Win. Thank you.
Thank you, Pak Win.
Okay, next is from David. Yeah, Pak David.
Okay, Pak Ivan, thank you, Pak Rigi, for the last session. From the topic, I was thinking that there is about turbidite sequence reservoir characterization. So from this screen, we know that the turbidite can be deposited and subtidal to the deep sea environment. So this is the clastic case. How about the turbidite of carbonate case? Can we interpret that from outcrop? It is the boundary, because sometimes the porosity generation from carbonate is driven by genetic. Can we trace that, Ivan?
Yeah, for this presentation and the studies, I used the classical outcrop from Brookcliff, but we can also use the outcrops from Padalarang, for the Raja Mandala formation, and probably scan them with the drones, and then we can, of course, we can see the porosity distribution within the carbonate facies, for example, and how the diagenesis develop in the outcrop. But of course, we cannot just use the filter outcrop. As you can see, the filter outcrop also has to be calibrated with sedimentary loss. So we have to also do a measured section within our filter outcrop, just to make them calibrated to what we see on the field. It's like that. After that, we can digitize each of the fag porosity or channel from the geogenesis, and then we can bring them to the 3D modeling as well. Yeah, so that is very possible with the carbonates and the turbidites also.
Okay.
Hopefully that's Andrew.
Thank you, Pak.
Okay.
Okay.
Thank you. Thank you, Pak David. Next
Thank you.
question from Bapak Ali Jambak. Yeah. Pak Ali, you can turn on your audio, please. Masih mute, Pak. Masih mute.
Okay, thank you very much, FOSI. I have the question and my comment. Your presentation is very good. Yeah, my question: the display your outcrop is very nice and often and clear from the topping of the forest. Yeah. How about in Indonesia, covered by forest is very difficult to the horizontal changes, phases and everything. Maybe in the Ngaraisiano, you can trace the Arau and Siloke. Can you explain how about the applied in Indonesia? In tropical area where the weather is very intense. Thank you very much. Can you explain, Ivan?
Yeah. We'll have to admit that when scanning the filter outcrop in the bookleaf is quite, I can say it's cheating, because the weathering in USA is very low.
Yeah.
It's almost like a desert-like climate in there. So in Indonesia, of course, the weathering and the vegetation are the main enemy when we're doing the filter outcrop modeling. When we are scanning the filter outcrop, we have to sometimes look for new road cuts. For example, if we go to Samarinda, we have a new road cut going through the what's it called, the stadium, new stadium in there.
Yeah.
Yeah. On the cliff to the right or to the left, we can see clear outcrops, and I'm very interested to scan the outcrop in there, and we can study the Miocene part of the Delta Mahakam from there, right? So that is the trick, to find the new road cuts, and then probably Harau.
Yeah, Harau. Brani formation.
Yeah, Brani formation. It's very interesting. We can directly link, probably directly link the structural generations, and then how Brani formation is deposited during the structural formation, and then if we can push our luck, maybe if we want to study the sawah tambang formation, for example, in Sawalunto, there is a very good sawah tambang
outcrop from the mining of tarmac.
Yeah, but the problem there is the vegetation, and you're right, and vegetation are quite difficult to to tackle here in Indonesia because of the climate. But it's not impossible. It's possible to be done here in Indonesia.
Okay, thank you.
Thank you.
Okay, Pak Ali, thank you. Yeah.
Yeah, thank you, Pak Ano, Ricky.
Yeah.
Okay.
May I make a comment?
Terima kasih.
Yeah. Yes, Pak Win.
That was an excellent question, and Indonesia is quite unique. It's not the book cliffs. So what I've seen, and the IPA used to set aside and try to focus on student papers that would come to the IPA. And more often than not, students would go out into quarries.
Yeah,
and they would, unfortunately for the students years ago, it was all bits and pieces, parts of maps. But there have been student studies where they've gone out and they've flown drones and they've put a lot of students on the outcrop, and you get a puzzle piece. And the power of what you're saying and doing is you can take an analogy that maybe has a lot more outcrops, and you can take one puzzle piece, a couple of quarries, and these students hammer the the heck out of these things and take a lot of samples, but it's still just a postage stamp. So when you put it into terms of the model and spatial relationships that you can hear now digitally, and you can start to insert that puzzle piece into the whole matrix. So I see a lot of applications for this, and there's probably a lot of students that would like to work with you and a drone and get out there and pull it all together. Just a comment.
Great, Pak Win. There's also you pointed a good point there, Pak Win. So we can flow the drones with the permissions from the owners of the quarries, for example, and then we can scan the cliffs within the quarries. Yeah, that will create a good virtual outcrop as well.
Okay. Is there any questions? Okay. I think that's all. Yeah, that will be end of our discussions. So thank you very much for all for coming to these sessions. This is very interesting. And from behalf of FOSI, Ricky, Melinda, and then Mas Erlangga, Pak Win, we are very honored to have Pak Ivan here, and also hope that you can continue this research in Indonesia, because we need more, because FOSI also have a program for FOSI Outcrop Atlas. We also want to manage to make a database for Outcrop Atlas. I think DOM or our digital outcrop model can be also included to the Outcrop Atlas. So we will be very happy if we can work together in the future, Ivan. Yeah.
Sure.
Yeah. Okay, I think that's all from me. Thank you very much, and Melinda for the closing.
Okay. Okay. Thank you, Mas Ricky, and thank you, Mas Ivan, for your time and sharing in FOSI. Maybe if you have another topic that to be shared in FOSI, we are most welcome for that. And thank you everyone for joining us tonight. And by next week, we will be having another talk about carbonates from Michael Moore City. And stay tuned in FOSI Instagram. And thank you very much. See you everyone.
Yeah, thank you all. Yeah, have a nice weekend. Yeah, bye.